Okay, let's get started. I'll talk about data compression today. This is discussed in chapter 5 of Carver and Thomas, second edition. Basically, data compression can be done with or without distortion. Chapter 5 is for data compression without distortion. Okay, that is, it is called distortionless data compression. The subject, which is data compression with distortion, will be dealt with rate distortion theory, chapter 10 of Carver and Thomas. So our class in our class, we have discussed data compression, especially in the materials for chapter 2. That discussion tells us that we would like to use a shorter description for frequent outcomes, longer description for less frequent outcomes of a random source from an experiment. A source is a collection of code. A code is a collection of code words. A code word takes an outcome of an experiment and maps it to a binary description or ternary description or d-ary description. Thus, a code is a map from an outcome to a binary string. A code well designed shall have a small description length. This minimum possible description length is the entropy of the source. A non-IID source can be described by the entropy rate and the conditional entropy, as we have discussed in chapter 4. A source code efficiently does this mapping, and the design of a good source code aims to attain a minimum possible description length. So a good source code has small minimum description length that is very close to the entropy. The expected description length of any code is lower bounded by the entropy or the entropy rate. Information sources include the data sources such as typewriter, signals, and telegraphs, as Carver and Thomas talks about in their textbook. A more modern examples would include news articles, blog posts, YouTube audios, manuscripts, and documents. The source code and the shortest description length of a random source are the subject of this chapter. Okay, here is the first item. A code is a map. A source code C for a random variable x is a mapping from set x to C. X is the alphabet of x, and C is the set of code words. Each code word, denoted as a C of x, is a finite length string of d-ary digits assigned to x, an element in set x. So in picture, it can be described by this figure. So the convention that I use here is this element maps to that element in set x. This element right here is also maps to the same element in x. And these three items, each one maps to that element in set x. So such a map is allowed in a map because a map takes an is defined to be taking an element in the input set and provide an output for that input element. That's the only requirement for a map. So that is the only requirement for a function as well. So a source code C is a map. Well, a source code C, I haven't talked about the source code. So source code part is right here. So that is a map. X is a map. And then from the alphabet of X, we define code. Code is also a map, but this time from set X to D star. So D star is a set of code words. Each one is made of 30 digits. Okay, so map from set X to D star. All right, so random variable is a map. Code is also a map. That's what this picture aims to explain. And then for each code word in set C, or D star, we have a string, and then string has length. So we let Lx to be the length of a code word, Cx. Then the expected length is defined to be this. Because x is a random variable, there is a distribution associated with it. In here, we call it P of x. And then P of x multiplied with the description length, the length of each string for each x. Then if I multiply it and they take the summation for the whole x, then this becomes expected length of the code C. So a string of a 30 digit is made of theory alphabet, which is defined this way. For example, a ternary string 012201 is a string of a ternary alphabet 0, 1, and 2. There is no other alphabet element appears. This string is made of this alphabet, which is ternary. So that is the definition of a code. Code is a map. Code is a function.